Hello Algebra class. I'm sorry I'm not at school today, but hopefully this video serves as a good substitute. I apologize for the video quality. This is the first time that I'm trying to do what I'm doing with the camera that I have. Today what we're going to talk about is arithmetic sequences, section 4.6, and what we're going to learn today is writing the terms of arithmetic sequences, graphing arithmetic sequences, and then finally writing arithmetic sequences as functions. Now first, to talk about an arithmetic sequence, we need to know what a sequence is. A sequence is an ordered list of numbers. Each number in a sequence is called a term. Okay, each term we could call a sub n has a specific position n in the sequence. So 5 is in the first position, so we could say n equals 1 there. 10 is in the second position, 15 is in the third position, so n equals 3, and then so on. A sub n just means a term in the nth position. For it to be an arithmetic sequence, the difference between each pair of consecutive terms would have to be the same. This difference is called the common difference. Each term is found by adding the common difference to the previous term. So if we look at this example, we start with 5, go to 10, 15, and 20. What we can see is, to go from 5 to 10, we would have to add 5. To go from 10 to 15, add 5 again. And then once again continuing that pattern. So adding 5 is that common difference. Okay, you see these 3 dots here. That means and so forth. So we would continue that pattern. Alright, these 3 dots are called an ellipsis. That indicates there are more terms in the sequence that are not shown. So let's go to that first example here. In example 1, it says write the next 3 terms of the arithmetic sequence. We start at -7, go to -14, -21, and -28. If we look for the pattern, we could see that we're subtracting 7 each time. Okay, if we're subtracting 7 each time, we could continue that pattern to get the next 3 terms of the arithmetic sequence. So we'd start at -28, and then we'd subtract another 7, and we'd get -35. Subtract another 7 to get -42, and then to get -49. So those would be the next 3 terms. Alright, for part B, it tells us the first term and the common difference, so we have to come up with those next 3 terms in the sequence. So we would add that common difference to our first term to get 15, add 13 again to get 28, add 13 another time to get 41. Alright, in example 2 it says find the common difference of the arithmetic sequence, so it's just identify the pattern. How do we get from 13 to 18, from 18 to 23, from 23 to 28? We could see we're adding 5 every single time. So the common difference would be plus 5. Alright, in part B, to get from 6.5 to 5 and 5 to 3.5, from 3.5 to 2, we could see we're subtracting 1.5. So the common difference would be -1.5. In example 3, it says graph the arithmetic sequence and figure out what you notice. So the arithmetic sequence here is 4, 8, 12, and 16. These are the terms. So we can write that list down in the term column. Alright, each one of these terms is in a specific position. So 4 is the first term, 8 is the second term, 12 is the third term, and then 16 is the fourth term. Alright, let's graph those points. 1, 4, 2, 8, 3, 12, and then 4, 16. Alright, if we look at what we notice here, these terms follow a linear pattern. Alright, that's what it is to be an arithmetic sequence. Alright, moving on to example 4, it says, does the graph represent an arithmetic sequence and explain? Okay, obviously we can see that this point is in the first position, the second, the third, and the fourth, and then we have the values, so 15 to 12 to 9 to 6. So figuring out if it represents an arithmetic sequence is all about finding the pattern, okay, if there is one. To go from 15 to 12, we'd subtract 3, from 12 to 9, subtract 3, from 9 to 6, subtract 3. So yes, this is an arithmetic sequence, and that's because the common difference is -3. Alright, for the monitoring progress problems, I'm going to have you guys skip those. If you want to do those on your own, go ahead. What you should notice is that this arithmetic sequence follows a linear pattern. And when we're finding the common difference and writing the next three terms, once again, it should have that same exact pattern. So let's move on to writing arithmetic sequences as functions. Okay, because consecutive terms of an arithmetic sequence have a common difference, the sequence has a constant rate of change. So the points represented by any arithmetic sequence lie in a line. You can use the first term and the common difference to write the linear function that describes an arithmetic sequence. So if we let a sub 1 equal 4 and d, the common difference, equal 3, we could find the rest of the numbers in the pattern. So we'd get 7, 10, 13, and so on. Alright, if we take a look at what we're doing here, a sub 1 remains constant, so that starting value is 4, it remains constant, and what we do is add that common difference. This common difference is 3, so we'd add the common difference once to get 7. Add the common difference twice to get 10. Now if we look at this, when we get to the second term, we're only adding that common difference once. Okay, when we get to the third term, we're adding it twice. The fourth term, we're adding it 3 times. So we could think about this. To find the nth term in the sequence, we're adding it n minus 1 times, the position minus 1. Okay, for example, if we wanted to figure out what number is in the 9th position, okay, we would take a sub 1 plus n minus 1. So the 9th position, n is 9. Alright, so we would add the common difference 8 times. 9 minus 1 is 8 times. So then if we try to figure out that number, we have 4 plus 8 times 3. 8 times 3 is 24, and if we add 4, we get 28. Okay, if you want to do this for yourselves, you can go ahead. Alright, so the equation in an arithmetic sequence is a sub n equals a sub 1 plus n minus 1 times d. Alright, it can be rewritten as, if we think about it in point slope form, we would have a sub n minus a sub 1, that first term, equals d times n minus 1. We're just rearranging the terms in this formula here, putting d out front, and then subtracting a sub 1 to get it over to the other side. This would be the equation in point slope form. This would be the equation in y equals mx plus b, or slope intercept form. Alright, moving on to example 5, we're going to write an equation for the nth term of the arithmetic sequence. Okay, so the first term that we see is 14. That's going to be our a sub 1. Then we just have to figure out what is the pattern. What happens every single time to get to the next number. Okay? To go from 14 to 11 to 8 to 5, we would subtract 3 every single time. So that means a sub 1 is 14 and d equals -3. Therefore, in order to make our equation, we have a sub n equals 14 plus n minus 1 times -3. Alright, so if we want to find a sub 50, we're going to plug 50 in for n. So that means 14 plus 50 minus 1, which is 49. And we'll do 49 times -3. So 49 times -3 is -147. So we'll do 14 plus, -147. There we go. That's better. And if we add 14 to that, we get -133. So a sub 50, that 50th term, is -133. This cuts out the time of finding every single term before a sub 50. Alright, if we want to do that in part B, we first have to find the common difference, which is adding 5 every single time. So d equals 5. And then figuring out a sub 1. That first term is 12. So that means a sub n is going to be 12 plus n minus 1 times 5. So if we want to find a sub 20, we're going to take 12 plus 20 minus 1, which is 19, times 5. There we go. Alright, 19 times 5 is going to be 95, so we're taking 12 plus 95, and we get 107, so that would be the 20th term. Alright, if we apply this to a real life concept here, let's take a look. Online bidding for a purse increases by $5 for each bid after the $60 initial bid. So the bid number, the first bid is going to be 60, the second bid 65, the third bid 70, the fourth bid 75. So if we want to write a function that represents the arithmetic sequence, first off, here's going to be our a sub 1, $60. Now we're adding 5 every single time. So that means d equals 5. So our function could be written like this. A sub n equals 60 plus n minus 1 times 5. Now we could simplify this to put it in slope-intercept form to make it a little bit easier to graph. To do that, all we would have to do is distribute 5 and then combine like terms. If we distribute 5, we get 5n minus 5, and then 60 minus 5 is going to be 55. So we're talking about 55 plus 5n. Alright, we could also rewrite that as 5n plus 55. Alright, that means our starting value is going to be 55, and we're going up by 5 every single time. So when we do our scaling here for y, notice that in part C it says the winning bid is 105, and we want to figure out how many bids there were. If we want to use our graph, that means we have to get up to 105 by the time we reach the top of our graph. Alright, if we think about the intervals, okay, there's 9 intervals here. 105 over 9 is about 11.6. So maybe we want to go up by 15s here. So this is 15, 30, right, 45, 60. Every single time we go up by 2, we're going up 30 units here. Alright, so by the time we reach this marker here, we would get up to 120. So we can estimate where this is going to be. So 45 is about here, 60 is here, so 55 should be about 2/3 of the way up. Alright, if we look at our x scale, if we go up by 1 every single time, we're only going to get to x is 8, and that's not going to quite reach 105. So maybe we want to go up by 2s. That means every single time we go over 1, we'll go up about 10 units. So here's 2, 4, 6, 8, 10, 12, 14, and this last one would be 16. Okay, so when we go up 2, we go up about 10 units, go up another 2, and then continue that process. We're going up about 2/3 of the way. Since each one of these is 15, and when we increase x by 2, we go up by 10, we're going up about 2/3 every single time here. Okay, we graph that function, and then finally answer the question. The winning bid is 105. Right, adding 15 to 90 would get us to 105 right here. So we could find that x is going to be 10 when y is 105. So how many bids were there? There were 10. Alright, so finally in closing, why is the domain of an arithmetic sequence the set of positive integers? If we think of the domain, that's the set of all x values, or the set of all input values that we're plugging into our function. The input values here is the position. So when we're talking about the position here, we've been talking about positive integers. So the position we could say is always positive, but that's based on how we're writing this arithmetic sequence. That's assuming nothing can be in the negative position. All right, if we want to write an equation for the nth term of the arithmetic sequence here, we can see that we're going up by 7 every single time, so that's the common difference. D equals 7. That first term that we're starting at is a sub 1, so a sub 1 equals 2. And then once again, a sub n equals 2 plus n minus 1 times 7, common difference. So a sub 50 then would just be 2 plus 49 times 7. And then once again, 49 times 7 would give us 343. So we have 2 plus 343, which would give us 345. All right, so that would be that term in the 50th position. All right, folks, good luck on your homework. Remember, the odds are in the back of the book. It's page 214, 3 through 39 odds, and then 45. If you have your textbook, please get it out. Let's start working on the homework. If you don't have your textbook, get together with a partner that does. Otherwise, you can go online to that Big Ideas website, and you can look at the textbook there. All right, thank you, and have a good weekend.